Oh, all right, so I wanted to start with first reviewing. So for a show of hands, if you can see my screen and hear my voice, would you mind just raising your hand for me, please? Okay, I got a few hands that are raised, so it looks like everyone is set up. Is there anyone that can hear and cannot see? This would be a great opportunity for me to fix that now. If you have a mic, or if you can type in the chat, I'm looking at the chat now. Okay, I'm going to assume at this point that most people can see or hear. If you can let me know otherwise soon, that would be a very big help to me. Okay, so let's start with reviewing really quickly. All right, chapter 7, the meat of chapter 7 is this new class of reactions that are called eliminations. All right, so we want to get comfortable with the elimination reaction. And the elimination reaction is where I take an alkyl halide and I remove I remove a proton that allows me to not only kick off the leaving group and an H, but I form a double bond. All right. So we talked about the fact that there's two types of mechanisms for this. All right, somebody's mic is on. Background noise. Okay, so there's two mechanism types for eliminations. The first is the E2. We said this is very similar to the SN2. This is a bimolecular elimination. The kinetics or the rate of that reaction depends on my equilibrium constant and the concentration of both the alkyl halide and the base. All right, so that means that if I pump in a larger amount of alkyl halide or if I add a larger amount of base, I'm going to be able to speed this reaction up. All right. We talked about the fact that these are all a one-step process. That means that all the bond breaking and forming steps occur all at once. So what happens to get things going is that the base is going to remove a proton. Those corresponding electrons in that bond are going to try to form a double bond while kicking off the leaving group. That's going to give me my alkene product and my potential byproducts. Okay, so we said base removes a proton. The electrons shared between the proton and carbon are used to form a double bond, and the leaving group is going to leave with 2 electrons. All right, the opposite mechanism for elimination is the E1 process. This is a unimolecular elimination, and the kinetics or the rate of the reaction depends on the equilibrium constant. I'm sorry, this is the, yeah, well, it's not really the equilibrium constant, it's the rate constant, all right, and the concentration of just the alkyl halide. So if I add more base to this reaction, nothing happens. Instead, if I do add more alkyl halide, the reaction will be faster, all right? So E1 is very similar to SN1. We talked about all the different types, all right? What's probably most important is the solvent has to be polar protic, and we need to beware of carbon cation rearrangements. Typically, E1 processes occur in 2 steps. First, I need to generate my carbon cation. So here in step 1, the leaving group leaves. And in step 2, the base comes in and remove a proton, and those corresponding electrons form a double bond, right? So in this case here, we get this. And here, for this example here, it did not matter which side we pull the H from. But you guys are starting to learn that that does matter, all right? In certain cases, which side we pull the H. But keep in mind, for this example here, it's completely identical. So either H will lead to the same compound. So we need to understand this ability of alkenes. And the trick here to think about is the more substituted your alkene, the more stable it's going to be. So if I look at the tetra substituted alkene versus the tri, the di, or the monos, the tetra substituted alkene is more stable. So basically, all I'm trying to say here is when there's more carbons attached to the double bond, you're going to have a more stable product. All right, you're going to train your eye to be able to recognize this. So the first thing that comes out of this chemistry or out of this understanding is the fact that zeta rule dominates reactions or elimination reactions, all right, you're typically going to generate the more stable alkene, which is the major product. The way that you generate the more stable alkene is that you're going to remove the proton from the carbon with the fewest hydrogens. So if I look at this example here, on the left-hand side, there were 3 hydrogens on this carbon, and on the right-hand side, there was only 2 hydrogens on this carbon. I'm going to pull the side from the 2 hydrogen side to generate this product here, which had a double bond in between those 2 carbons. This is a disulfide alkene. If I went from the side that had 3 hydrogens, instead I would form this monosubstituted minor product. All right, you guys have seen this, so I'm not going to keep belaboring the fact. All right, let's minimize this. Let's go over to the other set of notes that we had on this. All right, so we started to look at some reactions and being able to predict the major products. So if I gave you this alkene, this alkyl halide with this base and solvent, you guys told me the mechanism type was E2, and the major product is a zeta product where I pull an H from the carbon that had the fewest hydrogens. All right, we cover the mechanism here. Everything happened all in one step. All right, down here we had a Savolas's reaction that favors the E1 mechanism. So the Liebman group left to form a carbon cation that rearranged, that we grab a hydrogen from to form that alkene. All right. The same thing for this case. We did another Savolas's. We got a different product because of the way things were kind of substituted. And we realized here that I got the zeta product here now because carbon 3 only had 1 H, where carbon 2 has 2. So I'm always going to pull from the side that had 1 H to generate my major compound. All right, so what we wanted to start to work on today, I'm going to change this. This is known as the Hoffman product. Is there's another way to do eliminations. Is it possible for me to pull from the side that has the most hydrogens? All right, and there is. All right, and to do this, I need a bulky base. All right, and the bulky base that we're going to use right? Its name is lithium, or I'm sorry, we use the potassium tert oxide. All right, so let's take a look at that molecule really quickly. Let's make this a little bit bigger. Let's put that in the center.
So, Dr. Cooper, why is it called a bulky base?
Okay, because it's big. So it's really coming from the size.
And we'll always just use this one in this course?
Yeah, we'll just use this one. There's another one that's kind of famous, but it's fine to use this one. This is the one that we're using in upcoming tests. Right, let me get my, actually, let me do this. Something's up with this. I remember having this issue last time I was drawing here. All right, I'm gonna start with a whole new page. All right, so this is our bulky base. You guys know what a tert-butyl group looks like. All right, and this is gonna be the oxygen here. It's gonna carry a negative charge. All right, and there's going to be a positive potassium that's going to be attracted to it. All right, I'm missing a carbon on my tert-butyl group here. All right. So this is potassium tert oxide. Nobody really draws it this way. This is just an introduction to it. All right, typically, most people will just write TB. Okay. Some people also write it as just CH3. Let's put this in parentheses. 3, a C, and an OK as well. All right, all these describe the same thing. All right, and probably another common version to see this to just be the straight line angle structure form of it. I will have a tert-butyl group here. I will have my oxygen there. Instead of having an H on the opposite side, I will put a potassium here. So these are kind of like the common ways of showing potassium tert oxide. Right? These are huge letters. Okay, so let's take a look at an example now. Let's say I gave you the same example we had earlier, where we had a chlorine on here. And I react this down with potassium tert oxide. And most people just use tert-butanol for the solvent here. All right, if I gave you this, what would be the major product of this reaction? All right. Actually, I'm going to change the solvent because I want you guys to think of something else. I'm going to put DMSO here. But first of all, can you guys help me determine which mechanism type will be present here? All right. I know this has to be a what class of reaction? An elimination, right? Because potassium tert oxide has to be in base, right? Is everybody comfortable with that? Potassium tert oxide is always a base. This never exits a nucleophile. So because this is a base, this reaction is going to be in the elimination class. All right, so the way that I think about this first is that I want to think mentally, which mechanism type? Is this an E1 or an E2? Can anybody tell me?
E2.
This is going to be an E2 process. That's right. How do you know it's E2? Can you help me out?
The DMSO.
Yeah, okay. DMSO is a good giveaway. All right, let's go ahead and break down each of our factors in the reaction mechanism. What type of solvent? You guys told me polar A product. What type of alkyl halide do I have here?
Secondary.
Yeah, it's a secondary alkyl halide. Very good. All right, and I know that my compound is a base. Right? Let's put secondary. I cannot see my characters here. All right, so the trick here is that in the mechanism, I just need to make sure I pull from the right side, right? The base has to pull the proton. Do I pull from side A or side B? Can anybody help me out? This is A over here. This will be B on this side.
Would it be side B?
Okay. Let's just do some work on this then. All right, so the trick with the bulky bases, let's put this up here. Bulky base can only pull, or I should say remove, protons from carbon with the most hydrogens, right? The reason here is sterics don't allow to approach areas
So that's
with a lot
what
of
you saying for a regular base. From the carbons, but on the pull from the here.
yeah, it kind of went like a robot on me. I couldn't hear you. But I think what you're trying to say is that the bulky base does the opposite of your typical bases. That's why we use these, which is that they only can pull from the side that has the fewest number of hydrogens. All right, was that your?
Yes, sir. Yes,
Okay.
sir.
That's right.
When you label A and B, you just labeling the different carbons, right?
Yep, I'm labeling the carbons that have H's that could potentially be removed.
Okay.
Yeah, that's exactly what I'm trying to do. Okay, so in this case here, bulky bases has an issue with sterics. All right, so if I look at A, how many hydrogens on A side? What you guys tell me? Is it in the way?
2.
All right, there's 2 hydrogens on the A side. And how many hydrogens on the B side?
1.
Okay, that's 1. So I'm big and bulky, right? Is it easier for me to glide over 2 hydrogens, or is it easier for me to glide over 1 H and another carbon? What do you think is easier for me to do?
To the hydrogens.
Yeah, it's easier for me to glide over 2 hydrogens. So in this case here, instead of forming the zeta product, I formed a Hoffman product. Would push my double bond on the carbon that has the most hydrogens, right? So let's break down this mechanism really quickly. Let's redraw this. Right, so I'm gonna draw my hydrogen over here, and then that's the one that's gonna be removed now, right? And why did I select this one? This is the Hoffman product. There's not really a rule here, but the Hoffman product says that the base can remove that's not really the way I'm hoping that would look. All right, so let's go ahead and do that. I'm going to take my base. All right, I'm going to use the O version of this, right? Keep in mind that that potassium is just attracted to the chlorine. So I'm just curious to use the oxygen. All right, I'm going to have its 2 electrons. Grab one of the H's on the side. That was the fewest. The electrons in this bond are going to collapse to form a double bond, and I'm going to kick off my leaving group. So in doing so, I'm going to end up generating the compound in the box. All right. I'll get that compound there from there. All right. So is there any questions now with the fact that a bulky base is going to change which side you pull from?
So Dr. Cooper, on the test, would you ever ask us to draw the minor product of this, and then that would be when it goes and joins the other side?
No, I won't. I usually won't.
Okay.
I'm just more interested in, can you draw the right one, given the right base?
Okay.
All right, we're gonna try to do some questions where I mix things up here shortly. All right, so let's move on to our last little topic that we wanna cover right quick. All right, I wanna talk about this stereochemical relationship that we need, all right? So there's some stereochemistry that comes up now, stereochemical. Terms. All right, the first stereochemical concern comes with the E2 because everything happens at once here, right? The base can only remove a proton from carbon that is trans. All right, we'll just say trans because that's a common word. But the best word here to say is antiproplanar. The leaving group. And the leaving group here is the halide. All right, let's take a look at this really quickly. Move this to the side. All right, so there's only one thing that we have to also start to think about here is that when I do E2 processes, all right, that if there's stereochemistry drawn on the H's, it has to be opposite to the leaving group that's leaving. So I'm gonna make this a little bigger, put that in red. So let's take a look at this example here. So I can make this a little bit bigger. Oh yeah, okay. Give me a sec, something's up with my settings. Still small. Okay, so I want to deal with this molecule. Get my fonts a little bit bigger here. I'm going to introduce it to sodium hydride. All right, I'm going to react this in TM. All right, so this is a base. All right, sodium hydride is definitely a base. It's not even nucleophilic at all. Right, and it wants to pull a proton. All right, so I need to think about where are the protons. All right, so is there a question about the number of protons here? So let's take a look. So where can I move protons? Where can I remove the protons to form an elimination product? I need to look where. At my neighboring carbons to my leaving group, right? So this carbon has a leaving group, so I only can remove hydrogens from the neighboring carbon. So this carbon or that carbon, all right? So I'll call this side A again, and I'll call this side B, all right? So the zeta rule will dominate for this base. It's not bulky. So how many protons on side A here?
Two.
All right, one more time. How many hydrogens on side A?
One.
There's only one hydrogen here, right? Good, good. All right, and how many hydrogens on side B?
One.
Also one, right? So in this case here, it looks like it doesn't matter, right? But I've drawn stereochemistry now on those two carbons. That means that I need to think about the H's. If there's a wedge methyl, I'm sorry, if a dash methyl is here, that means that my H is on a what here, most likely? On a wedge, right? And over here, if there's a wedge methyl, then my H is on a what? On this side. On a dash, right? So we say now that there's a still stereochemical relationship that has to happen between these atoms, all right? And we said that the leaving group, which is the bromine that's on a wedge, and the H that we pull has to be on or has to have a trans relationship to each other. So which one has that trans relationship? Is it side A or side B? So this is on a wedge and the leaving group is on a wedge, right? So they have a what relationship to each other? This relationship, bromine is wedge and H is, right? So is that the relationship that we needed here?
No.
That's not the relationship that we needed, right? What about on the opposite side? What's going on here? That's my trans relationship, right? The bromine is wedge and the H is dash each other, right? So now it has the correct relationship to be removed. So in this case, there's only one H that can be removed, and which one is it? The H that's on my,
Dash.
go ahead, I'm sorry.
The H that's on your dash.
That's right. Or the H that's on my right-hand side. So the final product from this reaction would be this compound here, right? This is actually the only product that can form. Right? All right, is there any questions now with the stereochemical relationship? This is the E2.
Yes.
Okay.
Okay, so in reference to the previous problem, are you saying that when it's not a bulky group, you can choose any carbons that are different? Like, well, when it is a bulky group, you could choose any carbons that are different, but when it's not a bulky base, then you have to choose the two beside the BR.
No, I don't think okay. So you only can eliminate hydrogens neighboring the carbon that has a leaving group, right? So in this case, you have to always you have to think about what's going on at those carbons and what type of base you're dealing with. So here, the only two carbons neighboring this is a secondary alkyl halide. So there's two neighboring carbons, A and B. And in this case here, B only had one hydrogen and A had two. Because we're using a bulky base, we pull from the side that has the most. All right, we did an example earlier with the normal base that we pull from the side that had the fewest, that will lead to the zeta product. Down here, we have stereochemistry now. So whenever we do have stereochemistry at the neighboring carbons, we have to also consider for E2, we need to make sure we pull from the side that's trans. All right, whenever it's a E1 process, because there's a carbon cation, you lose this stereochemistry to the leaving group. So it doesn't matter. You typically will go back to zeta rule. You just rearrange if possible and pull from the side that has the fewest. All right, does that answer your question?
Yes.
Okay. All right, so this probably makes more sense if we start to just now look at an example. And see if we can kind of make sense of what is possible. All right, trying to see if I can make this a little bigger. This is looking weird today. All right, I want to change that right quick so I get the problem I want. All right, I'm going to take this compound. I'm going to react it with sodium methoxide and DMSO. I'll take the same compound and react it with sodium methoxide and water. And then I'll take the same compound and react it with potassium tert oxide. And I'll do this in EMF. Now, can you guys help me determine what should be the major products for these? All right, I'm going to give you guys a second to think about this, but you want to use all the rules that you have so far to make sense of this. For these three products, or these three reactions, can you tell me the major products for each one? Okay. All right, just in case, just because I put methyl, I'm gonna have to put methyl here. Just the spacing is just weird on these. I gotta change them. All right, just to be fair, I want everybody to recognize that it is a methyl there. Okay, I'll give you 2 minutes here. So 11:37. We'll try to cover these. But I want you to think about these to the best of your ability. Can you generate the major product for these three reactions? They're all the three same substrate. I just changed the conditions. One has sodium methoxide and DMSO, sodium methoxide and water, and then potassium tert oxide and DMF. What should be the major product? Okay, because of the sake of time, I'm going to go ahead and move forward. Does somebody have their hand raised? I see a hand up. Ms. Holloway, is there a hand raised? I'm sorry.
No, sir.
Okay, okay. All right, anybody else for anything? If not, I'll go ahead and get started. All right, so I see these problems. All right, first of all, I hope everyone is okay with the fact that these are elimination processes. These are all eliminations. So I'm not tricking you guys right now and mixing nucleophiles with electrophiles. I'm not going to be able to do that for this test. I'm not going to mix the two. All right, I'm going to tell you straight up, either this is a base or this is a nucleophile. And you should be able to know from that information what class of reactions I'm considering. Again, if I give you a nucleophile, I'm asking for substitution products. If I give you a base, I'm asking for elimination products. Okay, so if I look at my first compound up top, which is the same for all three, so it doesn't matter, I need to classify it first to give myself some type of clue to kind of understand how to do this. Okay, what type of compound or alkyl halide do I have here? Is it primary, secondary, tertiary, allylic? What does it look?
Tertiary.
Yeah, this one is tertiary. That's right. All right, and I'm hoping everybody is comfortable with the fact that this is tertiary, right? If not, I'm going to ask you to maybe find some time to come see me. I'm going to be available Sunday at 6 o'clock. So if there's still some struggles here, that's fine. Bring those questions with you, all right? But this alkyl halide is tertiary, all right? So that's very important to recognize. What type of base and what type of solvent do I have here? Strong base, and my solvent is which type?
Polar protic.
This is polar, but this is aprotic, right? H here. So what reaction conditions or mechanism conditions I'm favoring here?
It's in one.
Oh, these are all bases, so I'm not doing
Oh.
this. This is going to be the E2 mechanism, right? Okay, good. So this is an E2 process. All right. So mentally, and I'll see if I got time to go over the mechanism, but if not, at this point, I'm hoping you guys can start to do these mental. All right. I need to figure out which side I should pull an H from, right? So this is tertiary, so that means I have 3 neighboring carbons to the alkyl halide, right? So I got a methyl group that's neighboring. I have this carbon here that has a phenyl group, and I have this carbon here that has a methyl group, right? So how many hydrogens at position A? I'll call this B, and I'll call this C. All right, hopefully everyone can see that A has a total of 3 hydrogens attached to it. All right, B has a total of how many hydrogens attached to it?
1.
That's right, very good. B has only 1 hydrogen attached, and how many does C have?
1.
Also 1. Very, very good, right? So typical reaction faction is to pull from the side that has what? The most or the fewest hydrogens? That's right, the fewest, all right? I typically need to pull from the side that has the fewest number of hydrogens. That's going to be zeta rule. I only switch that rule up if I have what type of base?
A bulky.
A bulky base, all right? And my base is not bulky here, so I'm okay, all right? So now I have a tie between 1H and 1H, and this is the way you guys should think about it. If I give you a tie, you know that I'm not going to ask for both of those products most likely. So that means that there's something else there that we need to think about. And what's the other thing that we need to think about between the 1H's on both B and C? What's the second clue that we can use? So
Stereochemistry.
the stereochemistry, that's completely right. And so the rule says for any E2 process, I need to pull the H that's what relationship to the leaving group?
Trans.
That's trans. All right, which one has the trans H? Is it the phenyl side or position B, or is it position C on the methyl side?
B.
It'll be the middle.
Okay, so I'll just draw them in gray then if we need to. All right, because the phenyl's on a wedge, that means my H is on a dash here. What happened to that? Okay, so that's good. You guys hopefully saw that. It should be dash over here. But on carbon C side, I have an H that's on a what over here? That's wedge, right? All right. So what side can I pull from?
The side with the metal.
Good. So what should my final product look like? All right, I'm going to ask you guys to try this mechanism for yourself. All right, but my final product should look like. Like this. Double bond on that side. All right, this is going to be my product. All right, keep in mind, I see this mistake sometimes. I want to make sure you guys don't make the mistake. I probably won't take off, but still you should do it. That doesn't make any sense. Okay, it doesn't make any sense to put a dash at a double bond like this, right? Only carbons that are chiral should have a wedge or dash. Because I'm involved in a double bond, I don't have 4 unique groups. So that means that this should be a straight line coming to methyl, right? So you want to take a look at those small features when you are drawing your final product. But that is the product for this compound.
Dr. Cooper, would that other method be a straight line too?
Yep. Thank you. I didn't see that earlier. All right, so this is the final product or the major product from this. All right, and this came from Zeta's rule, but also my stereochemical rule right here, right? So maybe I'll put like a small box here so you guys remember. Right. This was the anti-perplanar H. Good. Let's look at the next case here. Can anybody help me out here? What type of solvent do I have? What type of alkyl halide? We already established as tertiary. What's going on with my base? We already established that it's strong, right? So my solvent here is which type? Rhodic, right? All right, so what type of mechanism type am I dealing with here now?
E1.
All right, this is the E1 process. So mentally, I need to think about the mechanism in my head here, right? So I know that the first step should be my leaving group leaving, right? Actually, I don't want to use red here. So I'm going to go ahead and draw my leaving group leaving. I'm going to draw that product out. If you can't see it, that's fine. You can draw it out on the sheet of paper. So when my leaving group leaves, I'm going to generate a carbon cation there. I'm going to draw my methyl back here, right? I took away the stereochemistry because my stereo center is sp2 hybridized. It has a shape that's trigonoplanar. So drawing a wedge and a dash off that carbon doesn't make a lot of sense. All right, so I get this tertiary carbon cation. And every time I generate a carbon cation, what should I think in the back of my mind? I need to think about rearrangements, right? Okay. So this carbon cation has next door a carbon that does have a methyl and a hydrogen. And over here, there's also a hydrogen. All right. So what type of process or what type of rearrangement most likely is going to occur here? So this is already tertiary. So if I do a hydride shift over, my plus will move over here, and this is still will still be tertiary. So it doesn't look like it got any better, right? If I did the methyl shift, that would be even worse because I go from something that's tertiary to now something that's secondary. So a hydride or methyl shift on the left-hand carbon doesn't work. If I go over here and do a hydride shift, now I go from something that's tertiary to something that's what over here? All right, I'm going to do the hydride shift here. All right, I go from something that's tertiary to now that's something that's tertiary and benzylic. So what is better? Does it be plain tertiary or to be tertiary benzylic?
The tertiary benzylic.
Tertiary benzylic, that's right. All right, so there's a
But
favorable.
Dr. Cooper,
Yes, ma'am.
on the left side, when you do the hydride shift, how is it not 4? Even though it's not a thing, but like when you add the H on the left side, how's it still tertiary?
Okay. So that this H would move here if I did that. Actually trying to draw that out. Let's see if I can draw it out for you. It would just be tertiary. So my plus will move there, right? And my H will move there. If I looked at my carbon cation here, I have a carbon that has a methyl group, this carbon up here, and this carbon out here. So it's just plain old tertiary. Does that help?
A little, but I'm still not seeing the difference from moving it to the left and to the right. Well, I get that it's by a pH, but as far as the
Yeah, that's the whole point. It's tertiary benzylic. That's better than just plain tertiary, right? This would be
okay.
so going from tertiary to tertiary, there's no benefit. So doing a hydride shift doesn't really benefit anything. But going from tertiary to tertiary benzylic is better, right? This phenyl ring has pi bonds that can delocalize that plus charge into it. So this is a 10 times more stable system. So we went from very good. Okay, good question. I went from a tertiary carbon cation, just plain, no allylic, no benzylic, to now something that's tertiary and benzylic. Right, and this is stable. So now when I think about the product that forms, because my carbon cation, which was in the middle, moved here, I can remove hydrogens from this carbon or from the bottom carbon. So let's go ahead and put my letters here. This is A side now. This is B side. All right, keep in mind, this is tertiary, but I can't remove any hydrogens from a phenyl ring because all those hydrogens are involved in double bonds. All right, so they're a little bit stronger than the norm. So bases typically can't remove. So which side would I remove hydrogens from? A side or the B side? All right, so A side only has one hydrogen, but B side has how many hydrogens? Two hydrogens on B side. So which side would I remove protons from? No bulky base, so I need to go with zeta rule. And zeta rule says pull from the side that has the fewest. All right, so I'm going to pull from A side. And so my final product is going to be that same proton that did the hydride shift is what the base is going to end up removing. So my double bond now will be involved with this compound here. I have a phenyl group here. Okay, and so I get this compound now as the product from that reaction. All right, so we look up top, I formed a double bond on the methyl side under my E2 conditions. On the E1, I formed a double bond on the phenyl side because of a rearrangement that occurs. And down here, what's going on here with this compound? This is my example with my bulky base, right? So we already established that this was a tertiary alkyl halide. I have a base that's bulky. And my solvent is which type of solvent? Polar A product, right? So my reaction conditions again are favoring what type of mechanism? E2, right? Okay, so I need to think about which side will I pull from, right? So again, I don't have to worry about generating a carbon cation and rearranging it and anything like that. I can just pull straight up hydrogens from any neighboring carbon to the carbon that had the halide. So we established that methyl is a neighboring, this side here, and that side there. All right. All right, so we just said that B and C both have one hydrogen each. Right? So this has one hydrogen. Also has one hydrogen. Piece isn't working. All right, and the methyl side has how many hydrogens? All right, I think everybody knows that a methyl group has 3 hydrogens. So which side will I pull a proton from? A, B, C, or D? I'm sorry, A, B, or C?
A.
Yep. I'm going to pull a and hydrogen from the methyl. So my final product.
So this one A.
Hello, hello. It's going to have a double bond to the methyl group up top. And that's going to be my final product for this compound. All right, so if we look at the summary, there's one similar substrate, depending on the reaction conditions, can give me 3 different products, right? So the trick here that we're trying to learn right now is to master the ability to be able to understand which product would form in which conditions that we give it, right? But that's pretty much the take-home point from this part of eliminations. Is if I have a bulky base, things are going to change, right? And I'm going to pull from the side that has the fewest number of hydrogens. All right, so that's going to conclude class for today. All right, I will host a Sunday review for exam 2. All right, I want to thank the students that did come by or did try to schedule office hours with me. There's a few students that came by, there's a few people that had to reschedule. But from those sessions, I realized that it looks like students need some more time. So I'm going to give you guys the weekend to try to put all the pieces together. Sunday, if you have any burning questions, please come by. I'm receiving a lot of emails sometimes about students saying they're having difficulty with classes and things of that. And it's good that you guys go and find help from other sources. But the best source of help right now is the person that makes your exams, right? So if you have questions and I can try to answer those questions, I can kind of guide you in the direction that you want to be in for your upcoming exam. So I highly recommend that if you guys can, please take advantage of office hours and opportunities to kind of set questions up to try to get clarity on things, all right? Again, I can't read your mind, and it's even more difficult with the fact that I can't even see faces, right? So when I hear silence, I'm thinking that you guys are telling me, keep going, right? Because I know this stuff. But then when I get people in my office, I realize that, oh boy, maybe things aren't grasped as the way that I thought they were. And that's fine. It's okay. We can work on that. All right. So stay positive. Keep working hard on this material. All right. For Sunday's session, I'm going to generate some questions on elimination. And then I'll have like maybe 4 questions where I mix eliminations and substitutions just to make sure that we can have our brain working on both types. All right, that's what you guys want to keep in mind. I need to know all the information for elimination, all the information for substitution, and I don't get thrown off based on what comes my way, right? I'm prepared to look at a question and determine if it's substitution and elimination, and I know all the intricate details among the two. All right, good, very good. I'm going to stop the recording. And I'll take any questions that anyone has.